high E, one of the last things that we'll talk about for Unit 1 is energy and keeping track of it and how it plays an important role in chemistry. There are some slides here that you don't need to write down, and I'll try and give you the heads up. But some of them I think will be important for how we look at energy in this class and how we track its changes. So energy is defined as the capacity to do some sort of work, and that work could be lots of different forms. Okay, every change in matter, whether it's a physical change or a chemical change, involves some sort of energy change or transfer. Okay. As I mentioned, energy takes lots of forms. Here are some of them. Maybe you are familiar. Like a car is a good example of a thing that has lots of different kinds of energy. You've got mechanical energy to make the parts in the car move, chemical energy in the battery that provides electrical energy, sound energy if your stereo's on, light energy coming from the headlights or from the dials in the inside of your car. The most important energy source or form for this class though is heat. We can transfer heat, we can track heat, we can calculate how much heat is lost or gained for any given chemical or physical change. So heat is defined as the energy that's transferred between objects of different temperature. And heat always moves from hot to cold. That's super important. I think people, when they especially here in Minnesota, when you have, in the wintertime, when you have when you go outside and it's cold and you put a hat on, that's not to protect your head from being attacked by outside cold. Instead, it's the exact opposite. You put a hat on to keep the heat on your near your body, on your head, because heat always moves from hot to cold. So when you go outside and you have a hat on when it's cold outside, you're losing heat energy. Or if you hold a snowball in your hand, the cold energy from the snowball is not attacking your hand to make it feel cold. Instead, it's the exact opposite. The energy in your hand that is warmer is leaving your hand and going into the snowball, and that feels cold. That's what sensation we call cold. So anyway, heat always moves from hot to cold. And excuse me, when you're tracking transfers of heat, you have to look at two areas. There'll be the system, which is the thing that you're studying, and the surroundings, which is everything outside the system. So you're tracking energy either going into the system from the surroundings or into the surroundings from the system. Don't worry about that. That is just an example of a diagram that we're not going to look at too much in this class. This is what I write down. If the energy is going into the system from the surroundings, that's called endothermic. Energy is going into the system from the surroundings. Endothermic reaction. So if you want to make a water boil, and water is your system, then you have to put energy into the water to make it boil. That's an endothermic reaction. You want to melt a snowball, and the snowball is your system. Energy goes into the snowball from your hand to melt it. That's the system. You have to be careful, though, what you define system and surroundings, because you can flip it around very easily and then just change your definition. So it's really important, especially if you take physics next year, to make sure that you're carefully defining what the system and the surroundings are. Okay, I already said some of those. Ice, melting ice, you get the idea. Oh, fun. I don't know why that's there. Okay, lovely. Exothermic reactions are ones that are giving energy from the system to the surroundings. So, for example, if you hold your hand over a fire, the fire is the system and your hand is the surroundings. Your hand feels that warmth. That's because the energy is leaving the fire and going to your hand. I think that's a good example. I can't think of anything else right now, but that's a good one. Oh, okay, sure. Freezing water. If the water is the system, when you put it in the fridge, remember, energy goes to the freezer, energy goes from hot to cold. So the molecules are slowing down. They're giving energy to your freezer, and that's an example of a exothermic change. Okay, lovely. Every chemical change, you don't have to write these down, but these are state changes of water. They all involve energy. So if you want to, all of the light blue ones, they are endothermic. You put energy into water to melt it. You put energy into water to evaporate it. All the sort of seafoam green ones, that is exothermic. A gas has lots of molecules moving really fast, and when the gas condenses, let's say steam condenses on your mirror in your bathroom when you take a hot shower, that's because the steam loses energy, and so that is exothermic. Don't forget that temperature is different from heat. Temperature is just really an indication of how hot or cold something is. And we measure temperature, it's the movement of particles. Literally, a thermometer measures how many particles are bumping into that thermometer. If a lot of particles bump into it, then that's recorded as higher temperature. And if less particles bump into it, it's recorded as lower temperature. So it's about how fast the particles are moving in a system. You can imagine putting a thermometer into like some boiling water. The molecules in the water are very hot, so they're moving really fast. There's a lot of collisions. But if you put a thermometer in a cup of ice water, the molecules are moving really slow because the water's really cold. And so as a result, that's what we say is, quote, a low temperature. In this class, temperatures measure 1 of 2 scales. We either have Kelvin or Celsius. They're directly related. Celsius is equal to Kelvin minus 273. Celsius is equal to Kelvin plus 273, sorry. 0 Kelvin is called absolute zero. That's no movement of particles. That's a theoretical thing. We can't actually make matter have no movement. We can get really, really close, within thousandths of a degree. But we can't really actually stop matter from moving, but that's absolute zero. 0 Kelvin. Maybe you've heard of, like, in space, it's absolute zero. It's very, very close to absolute zero in space because there's not a lot of particles and they're not moving very fast, but it's not quite absolute zero. Sorry, if you want to convert from Celsius to Kelvin, you add 273. I forget what I said 30 seconds ago, but there's the right one. If you want to, so here's an example. Convert 77 degrees Celsius to Kelvin, it would be 350 Kelvin. Just add 273. If you want to convert Kelvin to Celsius, you do the exact opposite. Take Kelvin minus 273. So if something is 167 Kelvin, if you want to find out what it is in Celsius, you just subtract 273 and you say, oh, it's negative 106 degrees Celsius. Notice this is kind of a minor point, but degrees for Celsius, degrees for Fahrenheit, but for Kelvin, it's just Kelvin. So something is 350 Kelvin, there's no degree word or symbol there. No negative values in the Kelvin scale. Remember, absolute zero is the absolute lowest a temperature could be. Who cares? And then this is what we just got into with specific heat. So we'll kind of, I think, end shortly here, but you don't have to write down different substances absorb and transfer heat differently. That's called specific heat. And I think that we're just about done. So don't write any of this. This we already have covered. I'm just going to scroll through here to make sure that you get all the stuff that's important. No. This is really fun. There's the Q equals MC delta T. Meow. And you don't need that. You don't need this. Oh, we're not doing that. So anyway, this is over. And all the scrolling on the last few slides was just like for funsies. Anyway, good chat. We'll see you soon. Okay, bye.